Hello everyone. In this video, we're going to study the derivative formula of linear functions. In the next video, we're going to study the derivative formula of quadratic functions. Some students may ask why we need to study derivatives, and they may also wonder if that's doable because derivatives that sound pretty advanced. Well, let me answer your first question. We do need derivatives. In macroeconomics, we're often interested in how one variable changes when other variable changes. For example, when we're discussing costs, then we want to know how much the total costs change when additional unit of product is produced, and that's called marginal cost. Okay. When we're discussing production, we want to know how much the output changes if the input increases by 1 unit, and that is called the marginal product of inputs. When we're discussing consumers' choices, we want to know how much a consumer's utility, or in other words, happiness, changes when additional unit of good is consumed, and that's called marginal utility. So we're always interested in how one variable changes when another variable increases by 1 unit. We refer to these concepts as marginal concepts, and they are very, very important in this class. If you're going to have a problem with these concepts, you'll find that you have a lot of difficulty in this course. So we need to find a way to study these concepts. It turns out that derivatives, they are the perfect tool to deal with these concepts. If we understand derivatives, then these concepts are not difficult at all. Thus, it's much easier for us to deal with these concepts when we're working on some questions. That's why we need to study them. Some students are still wondering, I guess, are derivatives difficult? Because we all know that calculus is pretty difficult. Well, I can assure you that in this course, I don't need you to use any advanced derivative theories, formulas. We only need 2 derivative formulas. One for linear functions, the other for quadratic functions, and that's all. And after watching this video, you'll find that, that's something I've already known. It's not that difficult at all. Okay, so let's discuss the derivative formula for linear functions. What's a linear function? A linear function is a simple function like that. No quadratic terms, no fractions. We only see numbers and a variable. Okay, and that's a linear function. X here, that's the input of this function, and this entire thing, which is equal to y, that's the output. And we call y the output variable. So intuitively, let's not talk about any calculus or anything like that. Intuitively, when x increases by 1, when this increases by 1, we can see the increase is magnified by this number, right? 1.5. Then now y is going to increase by 1.5, right? So we can write what we just said as an equation. The changes in y divided by the changes in x is equal to 1.5. Thus is 1.5 times of that. We need to understand that x changes first, and then it results in some changes in y. And the ratio is equal to 1.5. Not difficult at all. However, this is derivative. That's what we call derivative. Not difficult, right? Your math professor may give you a very rigorous definition for derivatives, but in this class, what does it say? The ratio of the changes in the output of a function to the changes in its input is the derivative of the function. If the changes are small, how small? Well, we're not going to give a rigorous definition here. In your calculus class, your professor will give you a better way to say this. Anyway, derivative means changes in y divided by changes in x, if we're talking about y and x. Later on, we're going to use other symbols, then we need to change these symbols. So that's the derivative. Now, when we're discussing derivatives, we don't want to write changes in y over changes in x all the time. We don't want to do that. We want to use some symbols so that it's easier, right? I mean, when you are doing arithmetics like 2 plus 3, you don't write the word plus every time, right? You use a plus sign. So we do the same thing here. We don't want to write changes in something all the time. We want to use a symbol to represent. For example, we're going to use delta y to represent changes in y, and delta x to represent changes in x. Here, that's delta. It's the Greek word for d, which means difference. So, now if you want to write something like that, want to write the derivative, we just need to write delta y over delta x. Now, remember, delta y, these two symbols, they have meaning only if we put them together. If we separate them, they have a different meaning, okay? Delta is not a number. It's not a variable. We cannot cancel it out in this expression because it's not a number, just like I said. Delta x does not mean delta times x because, again, I know I have said it a few times. It's not a number. Okay. In your calculus class, your professor will use d instead of delta. That's the correct symbol. But many students will take d as a variable because it looks more like a variable, right? Just to avoid that possible mistake, we're going to use delta here, okay? Because delta doesn't look like a variable. Hopefully that will help us avoid some mistakes. However, if you know calculus pretty well, then you're welcome to use d. That's fine. Okay, so we were talking about derivative. That's the derivative, and it's equal to delta y over delta x. How do we calculate it? Let's plug in y. It's y, right? Y is equal to 1.5x plus 3, and just now we said that that's equal to 1.5, because when x increases by 1 unit, the increase will be increased by 1.5. That's 1.5. Y will increase by 1.5. When x increases by 1 unit, y will increase by 1.5. So here's the formula. Whenever we see a linear function like that, we just need to grab the coefficient of the input variable and put it here. That's our answer. Some students will ask me, do we need to do any calculations from here to here? No calculations at all. Whenever you see something like that, just grab this coefficient and put it here. That's all we need to do. Nothing else. Now remember, don't draw arrows in your homework. Here I'm drawing it just to show you how it works. But in your homework, don't do that. Now remember, this is a constant, right? We don't have an x in it, so when x changes, this number doesn't change. Therefore, it's always 1.5. Now, if people ask you, what does the answer mean? What does the answer mean? Here's what it means. The answer means that for any value of x, when x increases by 1 unit, y increases by 1.5 units. Yeah. You may wonder where this 1.5 comes from. It's from here. This is the boilerplate part. We always write something like this. And then we write this part and we plug in this number here. Some students may ask me why we always use 1. You can use 2, but then you need to change this number to 3. Why do we want to do that? We don't want to do that. 1 is easy. Plus, we get to see a 1.5 here. It highlights our answer. So we're going to do that. Okay, let's look at some simple examples. Here we have a simple linear function, y equal to x plus 5. Then the derivative of it is delta y over delta x. Okay, that's the definition. Then we plug in y, which is x plus 5. It's here. Let's find the coefficient of the input variable. Oh, here, that's the invisible 1, right? Invisible 1. And then now we grab that 1, we put it here. That's our answer. Do we need to do any calculations from here to here? No, not at all. That's how the derivative formula works. So, if somebody asks us what the answer means, here's what it means. First, write this boilerplate part. The answer means that for any value of x, when x increases by 1 unit, y increases by 1 unit. Now remember, this one is the answer here. Okay, it comes from here. Again, when you are explaining what the answer means, you must first write this part, and then this part. Okay, now let's look at a different function. This is the demand function. We're going to see it in a few weeks, or maybe in a few days. We want to know the derivative of this function. It's defined as the change in d divided by the change in p. That's easy. That's the definition. There is nothing to say. Oh, I do have something to say. We must change the symbols. Here we have d and p, so we can't say y and x anymore because we don't have x and y here, right? That's the definition. Now let's plug in d. 12 minus 3.5p. Okay, so we have it here. Again, let's apply the formula. Let's identify the coefficient of the input variable, which is p. That's our answer. We just grab it, put it here. That's our answer. Do we need to do any calculations from here to here? No, not at all. Just grab this coefficient and put it here. That's how it works. What does the answer mean? Well, you can read this yourself. All you need to change the symbols, and this part is always the same. Actually, this is all the same. The only thing you need to change is to change this number and just set it equal to the answer here. There are no you don't need to be creative here. Just copy the sentence and change that number. That's all. Now let's look at this function. That's a supply function. S is equal to 2p minus 10. Here we need to change the notation. S, changing S over changing p. We plug in S, 2p minus 10 here. Okay, let's find the coefficient of the input variable. Whenever we see something like that, let's find the coefficient of the variable, and that's our answer. This is equal to 2. Okay. We don't need to do any calculations here. I guess some people are still wondering, do we need to cancel out the delta and delta? No, we don't need to do that. Do we need to divide this by p? We don't do that. This is something totally different. This means something like that. Changes in one thing divided by changes in another thing. Okay. The answer is 2. And here's what it means. When you're explaining what the answer means, yeah, at this point, I guess you don't need to be creative. Just copy the sentence and change the number to that. That's all you need to do. So now we know how to use the derivative formula. But here we have 2 remarks about it. First, we need to change the notation. Yeah, I've already said that. Second, we must, when we're explaining what the answer means, we must remember this part. For any value of x, yeah, because the answer doesn't change. It's always equal to this constant. So we need to include that part. This is not true for other functions. It's only true for the linear functions. That's why we want to emphasize that part. It's here. For any value of p, x, p. Don't forget that part when you're explaining the meaning of your answer. Okay, now let's learn something new. Let's use the numerical approach to verify the derivative formula we got above. Here we say when x increases by 1 unit, y increases by 1.5, or in other words, the changes in y is 1.5 times the change in x. Is that true? The derivative formula tells us it's true, but let's use a numerical approach. Plug in some numbers and see if that's true. This is an alternative approach. Okay, if we get similar answers, then it's good. Otherwise, we're gonna have some problem. Okay, to do that, to do the numerical approach, we first need to choose a value for x. We can choose any value we want. You can choose set it to 1, 2, 3, And here we're going to set it to 5. When x is equal to 5, y is going to be 10.5. Now let's let x increase by a little. Now remember, the definition says that if we're talking about derivative, the changes should be small. So we're gonna assume that x increases by a little. How little is little? It's really difficult to say, but let's say 0.1. In your homework, you can try 0.2, 0.01, 0.02. Yes, these numbers, they're small enough for our examples. Anyway, let's assume the change in x is 0.1. Delta x means the change in x. Given the new value of x, then the new value of x is 5.1. Given the new value of x, we have the new y. Okay. Then the change in y is equal to its new value minus its old value. So the change in y is 0.15. Given these results, we have this. The change in y over the change in x is equal to 0.15 divided by 0.1. That's 1.5. Okay, so it's equal to the result we get with the derivative formula here, 1.5. This is kind of like a toy example, but it tells us that the derivative formula is true, or at least it doesn't have a big problem. So this is all we need to know about the derivative of a linear function. Now we're going to see how you write the solutions for a homework question. In this class, you need to pay a lot of attention to the format of your solutions. Some people may say, "Oh, yeah, as long as I get the final answer, it should be okay." No, it's not okay. If you're only able to get the final answers, that's a very low level of understanding. It's pretty much like you're able to draw a lottery ticket. You get the right ticket. You don't understand the ticket at all. Just need luck, right? In this class, we want you to have a higher level of understanding. That is, you should be able to write neat solutions. You should be able to explain this to other people. That's a higher requirement. So whenever you're trying to argue that you just need to get the final answers, well, realize that we want you to get a higher level of understanding. That is, write neat solutions, be able to explain this to other people. Okay, let's look at this question. Here is a function. First, we want to find the derivative of the function. The derivative of the function is, well, first of all, whenever you write an equation, first you need to use some words, write down some words here to introduce it to people. You don't want to grade your readers with some symbols, right? You want to grade them with words, and that's a communication skill that you need to learn in this class. Okay, let's apply the derivative formula. We know that it's equal to the coefficient of the input variable, so that's 3. Again, we don't do any calculations from here to here. We just apply the rule, plug this, get this number, put it here. It's 3. The question asks you to explain what the answer means, so I should do that. The answer means that for any value of p, when p increases by 1 unit, QS increases by 3 units. I forgot to mention that. You need to change the notation. Here it says QS, so this is QS. Okay, so now we finished the first step. Now let's now the question asks us to use the numerical approach to verify the answer calculated with the formula. Okay, first we choose a value for p for the input variable. Let's say it's 10. If you want to, you can set it to 20, 30, that's fine. If p is equal to 10, then QS, the output is 20. Okay, let p increase a little bit to 10.1. In other words, it increases by 0.1. Then the new value of QS is 20.3. Yeah, do the calculations yourself. Given these results, then now we have the change in QS divided by the change in P is equal to 0.3 over 0.1. The change in QS is 0.3. The change in P is 0.1. The answer is 3, which is the same as the answer that we got with the formula in question A. 3 here, 3 here. Again, the answer here is equal to the answer here. That's true only for linear functions. Later on, when we're talking about quadratic functions, you'll see they're only close to each other. They're not exactly equal to each other. But here, for linear functions, we should write it like this. They're the same. Finally, would the value of the derivative be different when p takes different values? In other words, when would this number change if we choose a different value for p? No, because 3 is 3, right? It doesn't change. You can set it to 20. You can set p equal to 20, 30. This will still be 3. It doesn't depend on p. It doesn't depend on QS. It doesn't depend on anything. It depends on this functional form. We have a 3 here, so the answer is always 3. So here's our answer. No, because for a linear function, its derivative remains constant no matter what value its arguments take. So that's all I want you to know about the derivatives of linear functions. I hope that helps.